Good morning, everyone. It gives me great pleasure to introduce Professor David Mason, who is going to be presenting this morning. Professor Mason has been an Emeritus Professor in the School of Computer Science and Applied Mathematics at the University of Witwatersrand since 2010. Before this, he was Professor of Applied Mathematics for almost 2 decades. He's prolifically published, and his research interests include Continuum Mechanics and Fluid Mechanics and Elasticity. He also belongs to several scientific societies. He's a member of the Academy of Science of South Africa and a fellow of the Royal Society of South Africa. Today, he will be presenting on the Mathematics and Industry Study Group, which he established in South Africa in 2004. Over to Professor Mason.
Thank you very much, Yoko. I've titled Mathematics and Industry Study Group in South Africa yesterday, today, and tomorrow. Now, Mathematics and Industry Study Groups, they're an international organization. They were first founded at the University of Oxford in 1968 by Alan Taylor. He did a sabbatical in the United States and saw the very good contact between universities and industry in the United States. And when he came back, he thought we must do something about contact with industry in the UK universities. It spread to Europe. There's now the European Consortium for Mathematics in Industry, ECME. Most of the European countries have study groups. It just moves from one country to another. India is very popular in India, Australia, New Zealand, Canada, but 1 or 2 in the United States. In some countries it's caught on, in other countries it hasn't. In South Africa, the first study group was held in 2004 at the University of the Witwatersrand, and we continued at the University of the Witwatersrand each year until 2010, when we started alternating with AIMS in Cape Town. And from then until about 220, 1 year Cape Town, 1 year AIMS, 1 year WITS. Then in 2020, we held the first study group at the University of Zululand. And I think going forward, we'll move between the 3 universities, between AIMS, University of Zululand, and WITS. In 2021, we held a virtual study group. It was a big success, a Zoom platform. And then this year, 2022, we had a hybrid study group, partly on site and partly online. Before every study group, we have a graduate modeling camp. This is for graduate students, honors students, masters, PhD, and early career academics. It's at the same venue as the MISG. We started off with 1-day meetings, and now we've got a 4-day meeting, Wednesday to Saturday. Sunday's a rest day, and then Monday the study group starts. Now, the Center of Excellence in Mathematical and Statistical Sciences has got 12 focused areas. One of the focus areas is mathematics and industry, and I'm the focus area coordinator, and Eric Mubai is the junior focus area coordinator. Our main activity is the Maths and Industry Study Group meeting. There are 21 node universities in the center, and each node university is invited to send 1 academic staff and 1 graduate student fully funded to the MISG meeting, so that it's spread to other universities. Now, the design of a study group, it's a 5-day workshop from Monday to Friday, and it's held January or early February each year. And about 5 problems are posed by local industry. On Monday morning, the industry representative makes a 20-minute presentation, followed by 10 minutes questions. And then the participants split up into small study groups, and they usually work on the problem of their choice. If too many people are in one group, they work on the second choice problem. They work collaboratively on the problem until Friday morning. Each problem's got an academic moderator and student moderators. So now Monday afternoon until Thursday, we work round the board doing mathematical modeling, and at the end of each day, progress presentations by student moderators. It gives the student moderators good practice at making presentations. On Friday morning, we've got a report back session to industry, 25-minute presentation by the academic moderators, and the industry representative comments on the progress. Now the participants, there are usually about 5 international guests. They play a very important part. They're very, very experienced applied mathematicians, and the other participants, especially the graduate students and early career academics, learn a lot by working with these experts. There are about 20 academic staff, 1 or 2 postdoctoral fellows, and in the graduate students, about 30, all of whom have been to the modeling camp. Industry representatives, about 5, so about 60 people at the study group. And as we said, each node university at the center is invited to send a member of staff and a graduate student. Now, a very important point is that there's no registration fee because participants provide expertise free of charge. So unlike a conference, we don't pay any registration fee. And we try as much as we can to support participants by airfare and accommodation because they're giving their expertise. Now, this is some of the international experts from the rest of Africa. Dennis Ndanguza from Rwanda, who's brought in problems on Lake Kivu, and Verdiana Masanya from Nigeria. Quite a few people over the years, Alfred Owoloko, Zambia, in the early days, Mubanga Lombe. Then we always like to have someone from Oxford because they take an interest in the study groups all over the world. And Hilary Ockenden and John Ockenden, they were at the first study group in 1968. This year, Hilary Ockenden, we had a virtual afternoon tea with all the lady graduate students and lady academics, and discussed career opportunities and so on in applied maths. So that was very kind of Hilary doing that. Colin Please is the Professor of Applied Maths at Oxford University, a very experienced modeler. Brewer and John Chapman, they're also professors at Oxford, and they've come 1 or 2 times. Colin Please several times. Now in Australia, from Perth, Neville Fuchs is a regular attendant. Professor Neville Fuchs, Professor Graham Hawking from Murdoch University, and then Philip Broadbridge from La Trobe University in Melbourne. And they've had a lot of experience. Tim Myers, he's at a research center in Barcelona, Spain. And from time to time, he sends adverts about opportunities for PhD and postdoctoral study at his center. So he's a very regular participant at South African MISG. And Alistair Fitt was one of the early participants, is now Deputy Vice Chancellor at Oxford Brookes University. And then we've had several people from India, very welcome. Dhanana J. Vakasa, Satyachi Roy, and Sanjeev sadness. Then from Heriot-Watt University in Edinburgh, Andrew Lacey and Sean Bohan from Pennsylvania State University, and from the University of Limerick in Ireland, Sarah Mitchell and John Chapin were regular people. So these experts, we learned a lot by them participating. Now, there's a very important point about study groups. A study group is open and free from any non-disclosure agreement with industry. That means that we do not have any contracts with industry about publishing. We can publish anything that we work on. We can use it in our lectures and tutorials. The problems, therefore, are not secretive. They can be discussed openly in the study group. For example, problems like safety in mines. We don't keep these secret. They share with everyone in the mining industry. So they're the type of problems we work on. And that's very important from the publication point of view, because the participants want to get research papers. The industries which submitted problems, institutes and university, Sugar Milling Research Institute in Durban has submitted a lot of problems. The School of Mining Engineering at WITS has a lot of problems. Global Change and Sustainable Institute, WITS University. University of Rwanda, that's from the rest of Africa. The cement and concrete industry in the early days, and also in the early days, the Mine Health and Safety Council. Now the companies, Columbus Stainless Steel, Sapi Forest Products, Nedbonwana Mill. We went down and visited them one day. It was very interesting to see around the mill. That's in Mpumalanga. Element 6 Technologies, that's De Beers, that was diamond problems. PFG Glass was interesting problems on glass. Pebble Bed Modular Reactor, the nuclear reactor. South African breweries. Xylabs, it's a technology company in Johannesburg. And Apparate is a company that helps urban farmers and rooftop farmers. Now, the important thing is that work continues in the problem after the meeting. We have an executive summary aimed at executives, summary without equations, the full technical report by 30th of June. And we've got an online proceedings of the MISG, papers in international journals. We've got 31 so far. Now, there's this important point. Many staff do outstanding teaching, but little research. And these staff have difficulty in getting promoted. The established methods taught that the teaching the lectures, they can be applied to new industrial problems, and this can lead to publications. So by applying known methods to new problems, you can get publications and advance their career. Now, the Mathematics in Industry Reports, MIR, M-I-I-R. This is an online repository of reports from study groups from around the world. Now, it's supported by ECME, that's the European Consortium for Maths in Industry. And it started in 2020. It's hosted and organized by Cambridge University Press. So it's a new initiative, and the idea is we submit reports from the study group to MIR. Now, what's the advantages, the benefit of publishing study group reports in MIR? Well, they're fully searchable and free to access. Now, every report is assigned an individual DOI. Now, views and download metrics are calculated. So we'll see how many people are viewing the report and how many people actually download it. So that would be quite interesting. Then they've got a comment section on each report to allow feedback and collaboration. So that should be interesting, people commenting on the report. Now, we've got a dedicated space in MIR. We submitted 5 reports from MISG 2021. They say a light touch moderation. That means they review it, but not in great depth. Now we're waiting for the outcome to see what happens. And then we've got this important point. A report in MIR is not a peer-reviewed publication. It's a citable work with DOI and Google Scholar indexing. So we want to see if we publish or we submit a report to MIR and it's accepted, will journal editors still consider our paper? MIR says they will, so we've got to see what the outcome is. It could be that you've got a report that you do not want to take further. It's good work, but that you're dissatisfied with that, then submitting it to the MISG and Industry Repository is a very good idea. Now, there are many benefits to academics or to industry. Now, just this key one here, new perspectives and fresh ideas brought to a problem. Mathematicians, we look at the problem differently from say engineers or physicists, and various industry representatives. They've got responsibilities. They must be there throughout the meeting. Benefits for academics. So new lines of research can be opened up. It's not just the problem itself. It opens up a line of research. Publications and new research collaborations, and benefits for graduate students, scientific communication, making presentations, seeing how mathematical modeling is done. There's this one also, learn leadership skills by observing the way the moderator coordinates and works on a problem and sees how a problem's modeled. Now, I'm going to discuss in detail some problems. I've got 5, but I don't think we'll be able to get through 5. So maybe see how we get on. So a problem from the sugar industry. Now this was submitted to MISG 2012 from the Sugar Milling Research Institute in Durban. So this is an important research, important industry in South Africa. Now, they asked us to develop a mathematical model for drainage of molasses, that's sugar juice, from sugar crystals in a centrifuge, and investigate methods to enhance the drainage of molasses. Now, at the meeting, it wasn't until Wednesday, I think Professor Colin Please came in and said, I've thought of a model. So that's typical. You don't get the model in the first day. The model is sugar crystals lined up like this. This is on the side of the centrifuge. You've got the centrifugal force, omega squared R, causing the drainage. And this will be a thin fluid film between the 2 layers of sugar crystals. And we want to see how the fluid drains from that. So it satisfies a first order quasi-linear PDE. This is a good example of a quasi-linear PDE for lecture material or projects. It's the same as the flow due to gravity, but we've got the centrifugal force instead. And this is the fluid, the thin film draining from the sugar crystals. The initial condition is you've got a rectangular situation, and then it starts to drain. The solution consists of 2 parts. For Z less than T, get that, and for Z greater than T, we get that. And you can see why you get 2 parts. As it starts draining, it's going to reach the surface. That's one part of the solution, and this is the second part. And then it drains a bit more. And then eventually, this solution is going to reach the end point here. And then it'll start draining further, and a space will occur this will be at the edge of the centrifuge. And then it'll gradually get thinner and thinner. The main problem is that this moves quite quickly till here, and then it's relatively slowly from here. It behaves like 1 upon root t. For example, dV by dt is a constant, a third, when you're in this range, and it's quite slow. It's like t to the minus 3 upon 2. So how can you speed this up? That was what they were wanting to do. And we can look at characteristic times. The characteristic drainage time is 25 seconds. The Sugar Milling Research Institute said that this was a very useful result. If you spray with water, it's got a diffusion time of 80 seconds, so that's not very good. But if you spray with steam, you've got heat diffusion. Heat diffuses much quicker than water. And the characteristic time for heat diffusion is 0.6 seconds. And so our recommendation was diffuse, well, to increase the amount of drainage sprayed with steam. Another problem was the spontaneous combustion of sugar cane. I'm not sure if we'll have time to do that. So the recommendation was this. I'll just go back to this. If you've got a pile of sugar cane, they store it because it's useful as a biofuel, but it would combust spontaneously after about 50 days. If you've got this 5-meter pile, then the temperature increases slowly, and then it starts to increase. And here we've got thermal runaway after another day. So what the study group did was, instead of having one pile of 5 meters, you have a pile of 3 meters, and then another pile of 2 meters put on that. So this shows the pile of 3 meters after 1 day. Then you add the second pile of 3 meters. And then we see that we don't get runaway. So the recommendation of the study group was to make the piles sequentially. The reason why you probably don't get that is because the oxygen is at the top, and if you put another pile on it, you reduce the intake of oxygen. There's just this point here. All these problems have got extra problems. What happens if it rains and so on? So not one problem leads to another. Problems in the mining industry. They're very important in South Africa. Mining is the largest employer of people in South Africa. And one of the problems that was asked was about the support of mining excavations. They make a tunnel, and you put a shotcrete on it. It's a sort of cement that you put around it, and it supports the excavation. It's like a structural arch. But what they've been doing recently is they've been using thin spray-on liners, only 4 millimeters thick. Now, this isn't forming an arch. And they were wanting to know, why does this thin spray-on liner give such good support? This is the type of problem. This would be our, the liner. This is the rock mass, and this is the excavation, the tunnel. You've got matching conditions. We've got stress-free here, matching conditions, stress, normal and tangential stress, normal and tangential displacement. Oh, sorry, up here, this is the interface between the liner and the rock. So you've got all the matching conditions there. And then you can look at things like the rotation of a rock element. Now, this problem can be solved analytically. That's the good thing about it, that we can investigate it analytically. one works with the area stress function, which satisfies the biharmonic equation. The harmonic equation is del squared phi 0, biharmonic is del fourth phi 0. How do we solve this? We look for the asymptotic solution for large R. We see it behaves like sine 2 theta and R squared. So for the general solution, we look for FR, a function of R times sine 2 theta. And if we substitute this into the biharmonic equation, you get Euler's differential equation. So the power of R here is the same as the order of the derivative. And that can be solved exactly. So we can get exact solutions in the different layers. We get a perturbation solution, which is better to work with, which is the thickness of the liner over the radius of the excavation, epsilon. And this quantity E dash is the Young's modulus times divided by 1 minus sigma squared. Sigma is the Poisson ratio. Now we can solve the problems. We always get this quantity epsilon E1 dash over E2 dash. It comes in all the solutions. And we want to make that as large as possible so that the liner has some significant effect. So if we've just got a simple liner 4 millimeters thick, we find that this quantity is 5 times 10 to the minus 5. But if we investigate the real situation in which there are cracks, if this tunnel is excavated, the rock is cracked near the surface, and the liner will penetrate into the cracks, and that will seal the cracks. So how is this modeled? Before the cracks, we've got a Young's modulus, which is less than the Young's modulus in the rock mass. Because of the cracks. When we seal the cracks, the Young's modulus here is exactly the same as the Young's modulus in the rock mass. So you can solve these two problems and match and do the matching. And we find that this quantity, when you've got penetration of 100 millimeters into the cracks, you get epsilon is about 3 times 10 to the minus 5, no, minus 2. So it's bigger. We can begin to see how the thin spray-on liners contributing. This is the crack problem, but suppose they're really very long cracks, and the liner only goes a certain distance in. So to begin with, we suppose these cracks go to infinity. To begin with, we've got a reduced Young's modulus, and in this area, which is filled with the thin spray-on liner, the Young's modulus increases, and you can solve the problem for that case. And you find that this quantity that the solution depends on is 10 to the minus 1. So it's more significant, and we can see how the thin spray-on liner contributes to the stability of the mine. An important problem was the rock strength, brittleness, and blast fragmentation. When rocks are quarried, for example, to make a breakwater at the coast, the size of the rock is very important. You need large rocks for a breakwater or a harbor. And when you've got explosives, how do you know the size of the rock that you're going to get? Well, they use the Coase-Ram empirical model. Now they get the mean size of the rocks because we put the mean value into a distribution, a statistical distribution that gives the statistical distribution of the size of the rocks. So the mean is what we've got to calculate, and they use this formula. Q is the mass of explosives in a single drilled hole. RWS is the relative weight strength of explosive to TNT, to this power. This constant here runs from 0.8 to 22. And this, I think doing this is more an art than a science. And so I'm just can't remember what K is here. We haven't got it in the list. So when you've got a problem like this, what one uses is dimensional analysis. Now, just to save time, it's just the standard way in dimensional analysis. We ended up with this formula for XM. It depended on the yield strength, the speed of propagation of an elastic wave, that's the principal wave. Beta is a factor that describes brittleness, and E is the energy per unit time per unit volume of the explosive. So we managed to get this formula. We can introduce more physical quantities. You can introduce the time between the setting the explosives off in different drilled parts of the rock. This could be the difference. I'll just have to go back and just check what these are. B is the spacing between the charges, time delay between charge ignition at different locations, rock joint spacing. So you can have all these practical things. And then you get this basic part and then some function of these other constants. Now, this hasn't been tested experimentally, so we don't know how good it is. But it's just an example of dimension analysis when you've got a difficult problem like this. So I'd like to discuss an optimization problem now, because we haven't talked about optimization. And this was optimizing urban and rooftop farming in Soweto and South Johannesburg. Now, the difference between urban farming and conventional farming is that you've got small crop size spread throughout the city. You might have 100 people, for example, with all these small crops that have got to be collected. If you've got farming done with one or two big farms, you can just go to one or two big farms and collect everything there. But clearly, there'll be an optimum way to collect the produce from all the small farmers. There's another important point, that farming can be done year-round under controlled conditions. Because they actually grow it in greenhouses. It's quite sophisticated. We don't want all the farmers putting the produce, the same produce on the market at the same time, because that would drive down the prices. It's best if we can organize it so the various produce are grown at different times. So there's the two problems here. There's the routing problem and the problem of growing times for the crops. Now, this is the vehicle routing problem. Different produce requires different vehicles. Some vehicles must be refrigerated if you have refrigeration. And we seek a coordinated system that optimizes the routes between the farms during the collection of produce. And the predictive price model, farmers need to optimize planting and harvest time. The price of the product at different times of the year may influence the amount of produce. And so we need to avoid oversupply of the market. So you've got the two problems, and ideally we've got to combine the two. Predictive price model can be coupled with the vehicle routing model to get the best cooperation for farmers. Now, the study group worked on the vehicle routing problem. This is still to be solved. So the vehicle routing problem, the idea is minimize the total distance traveled. And this is the split multi-commodity vehicle routing problem. The split delivery vehicle routing problem, the restriction that the customer has to be visited once is removed. And the classical vehicle routing problem considers goods to be of the same value. Whereas the multi-commodity problem considers goods to be of different value. So this is quite a sophisticated vehicle routing solution that was implemented. And what they did was the three vehicles, two were non-refrigerated with different capacities, one refrigerated. There were 50 farms, longitude and latitude specified. It was in the Johannesburg inner city, the South Johannesburg and Soweto. And there's one depot. It was in the flea market, Johannesburg inner city. And they constructed a distance matrix between the farms using actual distances from a Google map. So all the farms requiring refrigerated vehicles, they were clustered into one group, and then the remaining farms were clustered into two groups. An objective minimize total distance, and the local search algorithm 2opt was used, and the minimum distance was 612 kilometers. And this is the 50 farms. Some are even up here in Midrand, Johannesburg, and down in Soweto. And then the farms were, as the location of the farms requiring refrigerated vehicles, they're quite spread out. So clearly, if you can optimize that in some way. And then this is those that do not require refrigerated vehicle. And they were divided into two clusters. And this is the final routes, the optimal routes for the three groups. I think one would need to see a colored map to understand this. So the routing problem was solved. The predictive price model for planting and harvesting times, clearly very important. Still to be formulated and find an effective solution, and then combine the two. Now this is typical of the reports in our proceedings. Part of the problem is solved, and then there's more work still to be done in projects and even masters and so on. Now, we'll just have a quick look at the problems over the last, since 2012, so 2004, 115 problems. 115. There's fracturing of rock with ultra-high pressure water. Can we do that? It would prevent dust coming up in mines. This led to a study of hydraulic fracturing, which is an important area of research now in the School of Computational Applied Maths. Coal mine pillar extraction. After they've mined it, they remove the pillars, and because the pillars are made of coal, so they do this in a controlled way, and by removing the pillars, the beams collapse in a controlled way. So this was Euler-Bernoulli beam theory, and we looked at the ways the beams fracture. They actually fracture at the supports, not at the midpoint. And then once they've fractured, sometimes they don't collapse, they form a voussoir beam, which we looked at. The fractured beams can still support For example, bridges going back to Roman times are still standing and highly fractured. And they're called voussoir beams. Now this, we can see 2020, the way things are going here, an algorithm for stoop boundary optimization for underground mines, how to plan a mine using optimization. You can see optimization coming in here, very important. It's not only rock mechanics. Tourism is the second biggest employer in South Africa after mining. And we looked at the value of domestic tourists in travel and tourism, how to optimize that, and developing South African Tourist Climate Index. This is a renewable energy wind turbine, and we went to a wind farm. That's when we were at Ames one year. Mathematical modeling of gas extraction from Lake Kivu, climate change, models for honeybee arrival and blossom phenology. The honeybees and blossom now come out at different times. Green roofs to mitigate the urban heat island, which was a very interesting problem. The one on rogue waves, they're large waves that can damage shipping off the coast of South Africa. And then we did one on masks, and the masks have even application in the environment. Now the conclusions, yesterday, it was always on-site. Mathematical modeling was important. There was sometimes optimization and image processing. The MISG today was virtual, hybrid MISG, still mathematical modeling. Tourism is also coming in, carbon capture, climate change, these types of problems. Well, tomorrow, it'll be on-site, but there'll be virtual subgroups at other universities. A good thing is we can get experts overseas online. We haven't done that in the past. Renewable energy, wind turbines, big data, we can expect that. And this is the organizing committee. People from all different universities contribute. Zululand, Stellenbosch, and Wits, and they are our sponsors. So thank you very much. So that completes the presentation.
Thank you, Prof. Mason. We will now move over to the question section. If there's anyone online who has questions that they would like to ask or comments that they'd like to make. Okay, so I'm told that Kendall needs to ask a question from the online audience. You can unmute yourself and ask a question.
Thank you very much. Hi, Prof. Thoroughly enjoyed your presentation. I think it's quite important that everybody gets to see what work is being done at MISG. I have a question. A lot of the time, students, especially that attend MISG, thinks that the problems end at MISG. When in fact this is not true. A lot of the time students can pick up problems as masters or PhD problems. How would you go about encouraging students that are maybe attending this talk or that will watch this talk in the future to go about picking up any of the problems that were not completely solved? Should they contact the group leaders of the problem, or how would you suggest that they go about investigating the problems further?
Now they should go to the MISG website and then go through all the proceedings from 2004 to 2021. And if there are any problems they're interested in, the problem moderator is the person to contact. Emails are usually given. The website is a bit complicated. Perhaps we can put it up at the end of this presentation. The reaction of the moderator it'll be either they're still working on the problem, they've got a student working on it, or they'll say, yes, that's a good idea, we'd like to work with you, or the person might say, well, go ahead, I've moved on from this problem. But many of the problems are unfinished, and there's scope for honours projects and masters and PhDs. Yes.
Okay, we have seen a few questions in the chat. One was from Professor Clark, asking Prof Mason, usually how many problems do you receive for the workshop? So how many problems do you?
About 5 or 6 problems. It's usually quite difficult to get problems. We're very pleased to have problems submitted. About 5 or 6. And if there's 60 people, it means about 10 people working on each problem. We don't like the groups to be too large.
Thank you. A quick question from me before I take the question from the audience at the venue. I just wanted to know, in the past, have there been students who've undertaken MSCs or PhDs on any of the ideas that were discussed at the study group?
Yes, there have been quite a lot. I think Montaz has had at least one student. I've had several students working on the hydraulic fracturing. Dr. Fario, for example, Dr. Gatley in the school. Yes, and there was one student did a master's on the problem submitted by PG glass. It was the thin film of glass flowing out from the furnace, and successfully got a master's. And you know, you acknowledge at the beginning that the study group attended it, and it gave me some initial understanding of the problem, and then they went on and did the master's in that. Yes, there'll be 1 or 2, maybe not as many as one would want, but there have been several successful ones, and they're actually listed in the website, the students who have been successful in Masters and PhD.
Thank you, Prof Mason. That sounds very promising. I see lots of interesting topics that you've highlighted in the discussion today, and I'm sure that you will get many more interested people for PhD and MSc studies. I did see a hand in the audience. If you can introduce yourself and ask the question.
I'm Professor Ruma.
Hello, hi everyone. Hi, Prof. It's Rahab here. Thanks for the great presentation. I think it's good for everyone to see sort of a wide range of different problems that are solved at the study group. I just wanted to it's a comment, it's not a question. I just wanted to comment on, you know, particularly for students experiencing MISG for the first time, so those who would be doing it for the first time, that sometimes it may be it might seem like it's a little bit overwhelming, because you will have, you know, these problems that are, you know, that sort of require like vast knowledge on different concepts, some of which you've never been introduced to. But to say, you know, even when that's the case, it's actually an opportunity to learn something different. And also, even when you can't, maybe there's something that you didn't know you're going to learn, like some maybe mathematical concepts that you didn't know you will learn. But also note that some of the topics that you've already learned, they will, in some of the problems, they will be applicable. So, like, you know, simple concepts such as non-dimensionalizing can really have a big impact on how the problem is solved. And also to also note that problems are not always solved. Like, sometimes the solution to a problem is not necessarily mathematical, but there are also sort of creative solutions, like as you know, as Prof Mason has mentioned in some of the problems required creative solutions as opposed to mathematical solutions. You know, such as when they were talking about bagasse and staking it in, like, you know, multi-staking over some time. That is not something that comes from the mathematics. It's something that, you know, is a creative solution. So to students who are doing it for the first time, don't get overwhelmed by the fact that you won't know a lot. There will be lots of professors, lots of tutors, lots of, you know, industry representatives, and lots of experts that will help you in order for you to also engage and learn something and be able to contribute to the groups.
Yes, that's a good point, Rehab. There are lots of things, even if a student is getting a little lost, they can do literature searches. To develop a skill in literature research will be something very valuable. They can do the presentation, the project presentations at the end of each day. I once had a student who asked one of the very eminent professors, how do you do mathematical modeling? You know, in working with someone for 5 days, you can ask these types of questions. And, you know, and the reply was, well, they're doing a lot of modeling. You know, the experience you learn in one model, you can use in later models. But you can talk to the visitors and other academics and learn things that way, as well as the mathematical methods and modeling that you'll learn. And you also see how a problem is formulated from scratch and how it's formulated mathematically and how it can be simplified by mathematical modeling into a tractable problem, numerically or analytically. Yes.
Okay, thank you, Prof. We have one question from a member of the audience.
Yes, Professor Mason, good afternoon. No, good morning. We are still in the morning. This is Jean Lubuma.
Yes.
Thank you very much for your presentation. You have survived for many, many years with this group, which is very good. I just want to make a comment about what you think about the future. You were saying about tomorrow. And I saw in the list of options or opportunities in future, you listed big data, which is very good. And actually what I wanted to suggest or find out from you, I think that in future it is very important to go to this current move, which is towards a transdisciplinary research, whereby all the problems are not necessarily don't necessarily involve mathematicians alone. We need to involve people from social science. For example, when you talk about climate change, you know, climate change is a concept which is considered in many ways, depending on the discipline. When you're talking about big data, so what I wanted to suggest is that in future, I think that the group should be open to collaboration with people who are not necessarily from industry, but also who are from law, who are from social science, who are from for example, all issues regarding sustainable development goals. So I think that it is very important to consider that as a possible avenue for future. Thank you.
Well, thank you, Professor Lubumbo. That's a very good idea. In the past, yes, we've been working with engineers, and the climate change we worked with in the geophysics department. But in tourism, for example, we'll be broadening out, I think, into other areas such as the social sciences. Yes, well, even law, I hadn't thought about law, but I think the lawyers have got a lot in common with mathematicians. So we're open to any problems. It's difficult to get a problem. Some way, I mean, it's difficult just going and knocking on someone's door. You've got to get some sort of introduction or some way to get things started. And once you get started, a good indication of whether you were successful is if they come back for a second year later and bring another problem. And a lot of people have. So it's a good idea to broaden the people that we talk to. The institutes in the university, they're a source of good problems. Thank you, Professor Lubumbo.